High above the street, steel and concrete come together to build our cities. But when invisible stress builds inside these materials, are the regulations written in 29 CFR 1926 the only thing standing between a stable skyscraper and a pile of rubble? Before we dive in, please note, this video is for educational and forensic analysis only and does not constitute engineering or legal advice. In high-rise construction, investigators often point to the million-dollar gap. A site can pass basic inspections, every worker might wear the required personal protective equipment, and they might all carry their OSHA 30 certification cards. Yet, job sites that appear completely compliant on paper still suffer massive, catastrophic building collapses. Standard safety protocols focus heavily on the Focus 4 hazards, managing specific, localized risks like individual falls or electrocutions. But the invisible physics of load distribution across thousands of tons of material require a different perspective. To prevent structural failure, we have to look deeper into the mathematical demands hidden within the regulations themselves. Survival on a high-rise project requires treating OSHA 1926 as a rigid blueprint for managing gravitational physics. The rules governing these massive weights are primarily found in Subpart Q for concrete and Subpart R for steel. Together, these sections establish the structural framework designed to counteract the forces of wind loads, the pull of gravity, and the threat of progressive failure. This diagram illustrates a highly vulnerable phase in construction known as green concrete. When a top slab is newly poured, the wet material has not yet reached its design strength. It must temporarily support its own massive weight without fracturing. To keep the structure intact, Section 1926.703 dictates the use of temporary shoring. These engineered pillars sit directly beneath the green slab, absorbing the heavy downward forces and ensuring those loads are transferred safely down to the older, fully cured floors below. But if that complex load redistribution is miscalculated, or if reshoring is removed too early, the temporary pillars buckle. The green slab sags and snaps the floor beneath it, initiating a deadly cascading chain reaction all the way down to the foundation. Ignoring these precise load-bearing calculations transforms temporary support structures into the primary triggers for total building failure. This photograph shows the devastating aftermath of the 1987 L'Ambiance Plaza collapse in Connecticut, where concrete slabs stacked violently into a pile of rubble. This project used a lift slab method, where concrete layers are poured on the ground and hoisted up vertical steel columns using hydraulic jacks. The forces involved in lifting thousands of tons are unforgiving. OSHA Section 1926.705 specifically mandates that lifting jacking equipment must be capable of supporting 2.5 times the anticipated load. Forensic investigators found a catastrophic loss of support at a single lifting jack in the West Tower. The mechanical assembly lacked the necessary structural capacity, causing an entire package of 3 upper-level floor slabs to drop instantly. A single, localized point of failure in a temporary lifting mechanism instantly bypassed all other safety measures on the site. Mechanical capacity is the ultimate safety net, and when it failed here, 28 workers lost their lives. 32 years later, another collapse demonstrated the same deadly physics. Looking at this view of the 2019 Hard Rock Hotel disaster in New Orleans, you can see the severely damaged, drooping upper floors of the steel and concrete framework hanging dangerously over the street. Following the collapse, OSHA investigators identified a severe engineering flaw at the top of the structure. The lead structural engineer had spaced the load-bearing columns on the 17th and 18th floors too far apart to handle the actual weight of the building. But the breakdown extended into the field execution. Under Subpart R, Section 1926.754 requires maintaining structural stability during erection. The steel erector failed to properly connect the beams to the columns, deviating from the already flawed contract documents. The initial engineering design contained mathematical errors, and field-level deviations compounded the stress. When those two factors collide, the resulting structural instability becomes a mathematical certainty. Preventing these disasters requires building a bridge between theoretical engineering and field reality. Within OSHA 1926, the ultimate defense lies in the operational distinction between two critical roles, the qualified person and the competent person. The qualified person holds a recognized engineering degree or professional standing. They calculate the physics, determine the load paths, and design the complex formwork necessary to keep the structure standing. The competent person is the boots-on-the-ground expert. They are capable of identifying existing and predictable hazards, and they possess the specific authority to take prompt corrective action, meaning they can halt a concrete pour the second a shoring post shifts. True structural prevention requires a constant aggressive feedback loop between these two roles. Pre-pour inspections and reshoring sequences must be coordinated daily to ensure the field reality matches the engineering theory. By rigorously verifying physical structural connections against the exact contract documents, teams can identify and stop the compounding errors that lead to historical tragedies. Regulations only save lives when they are understood, applied, and verified on the ground. Use 29 CFR 1926 as a diagnostic tool for structural safety. If you want to learn more about OSHA 1926, structural safety, and preventing catastrophic failures, subscribe to the HSE Study YouTube channel. An approved blueprint is only a theory. True high-rise safety is the exact, uncompromising execution of that theory in reality.